Hi folks, Mr. Long here. We're going to do a screencast on vectors and what vectors are. Vectors are, the simplest way to think about a vector is that it's a linear translation between 2 points. That's it. Moving something from one point to another. That's a vector. The direction it goes in and how long the translation is, right? That's a vector, a linear translation. And we're going to use that as our example today and carry through a whole bunch of basic computations about vectors. So let's go. All right, so vectors are linear translations. You can see I wrote that at the top. So this is based on a handout, so hopefully you've been able to print that out or you've got a digital copy that you can fill in. So to begin with, what we're going to do is we're going to take this object here at point A, and we're going to move it to point B, okay? And we're going to draw a vector to describe that. So it's at an ordered pair, and we're going to go to another ordered pair, and the vector describes that translation. So if I had a dot down here in the far right of the corner, or the far right corner, at 16, 2, and I wanted to move it, pick it up and move it to 10, 5. Okay, and I look across, that's 5, right? The vector describes that translation from A to B. Okay, from A to B. So what we're going to do here is describe our vector this way. So what we would do is just be drawing a straight line, and I put an arrow on it to denote that I'm moving from A to B. That, folks, is a vector. That's a vector. And we name vectors in a variety of ways. One of the ways we can name it is we can start here at A, and since we end at B, we write AB. Now, what I do is I write over top of it, I write a vector symbol, okay, a vector symbol like that. And so that denotes that that vector describes the movement of, or the translation of an object from A to B. That's a vector, AB, starting at A and ending at B. So let's go over and just describe a vector. So we've got this right here. So the way vectors are described is, so you can see here where the arrow is, where the point of it is, that's called the tip of the vector. Where the vector starts is called the tail. Okay, that's the back of the vector. So that's the tail, or that's where the vector starts. So it starts at the tail, ends at the tip. So we're calling this point F here and point G here. Now, how do we describe vectors? Well, a picture of a vector like this, just a picture, is called a geometric vector. So often when you solve problems in physics, it's called a geometric vector problem, right? You just have a picture of the vector. It's a force maybe, so a force is 10 newtons, so it's equivalent to like 10 units, whatever, force units long, and it has a certain angle, right? That's a vector. So a geometric vector is a picture. It can be scale diagram, it doesn't have to be, but geometric is a picture. When we start to talk about vectors in terms of x and y, that's called a Cartesian or algebraic vector. Cartesian or algebraic vector. And the way we describe vectors, not by x, y, but by delta x and delta y. How much does x change by? How much does y change by? So, and it's always, again, from the tail to the tip. Okay, from the tail to the tip. So if we look at this vector here, I had to travel along this path. Right, I started down here at F, and I end up at G. How much did x change by? Well, starting at letter F, I had to change by 3 units to the left. 1, 2, 3 units to the left. We call that delta x. So since I went left, I changed position by, so vectors are very much related to slope. Okay, folks, slope, delta x, delta y. So, and again, it's always from tail to tip. So delta x is 3, so I moved to the left by 3. Then what I did is I moved 1, 2, 3, 4, 5 up. Delta y is positive 5. So I would write that as delta x is negative 3 and delta y is 5. Now, if you notice, you can see these little These brackets are different. They're not round brackets. Round brackets denote locations. Okay, like an ordered pair. That's a location. A vector is not a location. I'm going to repeat that. A vector is not a location. A vector is, in this case, a change in location, right? That's why it's related to slope. It's how things are changing. So to go from F to G, you go 3 left and 5 up, okay? So again, some things that you need to know. What's the tail of a vector? What's the tip of a vector? What's the notation we use for a vector? Okay, this notation right here I'm showing you is American notation. It's also used in some provinces in Canada. Just so you know, another notation that could be used in Canada is square brackets, -3, 5. Okay, that could also be used. And then there's a British notation as well, which is my favorite, or European notation, which is my favorite notation. I find it easiest to work with, and we're going to work with that as well. I think it's important to work with all the different notations. For those of you going off to university, first of all, most of the textbooks that, if you're going to be using vectors, like in physics or engineering, they're not all, but many of them are American. And so you're going to see American type of notation, but you'll also see European notation because you'll have professors from Europe, right? So again, you'll learn that once you go to university, it's a very much an international enterprise, and you'll have professors from every corner of the globe, which is part of the thing, part of the reason it makes it so great. Okay, so let's go back here, and now what I want to do is I want to make another vector, this time from C to D. So from C, which is at 16 and 12, that's right here. And I want to make it to D, which is at 10 and 15. So I've marked on those points. C, I should bring that back this way. Okay, so we can get there. So I'm going from C to D. So let's take a look at this and just draw in our vector from C to D. And again, remember that that is the tail, and this is the tip of the vector, and we would call this vector D, CD, starts at C, ends at D. And I want you to notice something. Let's now take a look at this and figure out what delta x and delta y are. So delta x in this case equals 1, 2, 3, 4, 5, 6. 6 to the left, that's -6. Delta y equals 1, 2, 3. Delta y equals 3. What do we notice about AB? And in fact, by the way, these right here, delta x and delta y in and of itself are both vectors. Okay, this vector here is -6, 0. This vector here is 0, 3. Okay. All right. So going back down to here, what's delta x for this vector? 1, 2, 3, 4, 5, 6. -6. Delta y is also 3, same as the one above. So what do we notice about CD and AB? So let's write it in. CD vector equals delta x, delta y, right? That's the way we name a vector. It's -6, 3. But it's also, if we look here, AB is also -6, 3. Look at that. They're exactly the same. -6, 3, -6, 3. Notice that they start and end at totally different locations on a Cartesian coordinate system, but the vectors are the same. They're equivalent vectors. That is such an important idea to learn, because what it tells you is that vectors do not depend on location. They only depend on change in location in this case, right? Direction, vectors have only two things, a direction and a length. That's it. Two things, a direction and a length. They're not attached. You can attach them to certain points, but they don't have to be in that area. They're free form. They're free to move around. Okay, as long as they have a direction and a length, they can be anywhere on a Cartesian coordinate system. So, if the translation is the same, the vector is the same. That's really what's important here. Okay, so what we're going to do there is stop now, and then we're going to go through all the questions on the handout that are all about vector AB.